As physicists, we've eagerly anticipated this moment for over a century. Ever since 1916, this event marks a groundbreaking achievement, offering a glimpse into one of the universe's most intriguing and enigmatic phenomena, black holes. These cosmic giants, known for their immense power, remain incredibly elusive. Despite the enormous size of their gravitational influence, they are nearly invisible to us, making them even more mysterious. One such black hole, possibly weighing between 2 and 4 million times the mass of our Sun, is the subject of this discovery. Over the past few decades, research devoted to black holes has transformed our understanding, taking us from a position of absolute ignorance to one where we are starting to get an intimate look at them. And now, things have taken an even more thrilling turn, as physicist Michio Kaku has revealed that we have finally managed to peer inside a black hole. This revelation opens the door to a wealth of new information that could illuminate aspects of science we may have previously overlooked. Let us take a deep dive into the realm of black holes and discover what they contain. While space is boundless and vast, the concept of black holes generates numerous questions. Before we dive into the specifics of Kaku's remarkable findings, it's essential to understand the fundamental nature of black holes. Most people have at least a basic understanding of what black holes are, but significant gaps in our knowledge still remain. The theory of black holes originates from 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes, though at that point, the concept was only theoretical. It wasn't until about 50 years later, during the 1960s, that concrete evidence for their existence first became apparent. Researchers studying the constellation known as Cygnus observed an anomalously bright blue star emitting X-rays. This star, they discovered, was not stationary but instead was orbiting a massive black object. Upon further analysis, it became clear that these X-rays were being drawn into this object, leading to the coining of the term black hole. This discovery was a monumental turning point because it confirmed that black holes were not simply an invention of Einstein's imagination. They were real, tangible entities that existed in space. It became evident that we needed to study them more thoroughly. Scientists from around the world began focusing their research on a particular black hole in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years away from Earth. This black hole was about 14 times more massive than the Sun and exhibited extreme density, with a gravitational pull so intense that even light could not escape. This defining characteristic, the ability to trap light within its gravitational grasp, makes black holes both fascinating and terrifying. A black hole is a region in space where gravity is so powerful that nothing, not even light, can escape. Any object that ventures too close to a black hole is sucked in, and once it crosses a critical threshold, it is lost forever, never to be seen again. This inherent danger is why it's so critical to expand our understanding of black holes. After the discovery of Cygnus X1, researchers began an exhaustive search for other black holes, and estimates now suggest that there may be over 100 million black holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are exceedingly difficult to detect, meaning we don't have a precise count. What is clear, though, is that millions of black holes could be present within our galaxy, underscoring their importance in cosmic research. The main concern surrounding black holes revolves around their gravity. Their gravitational force is so immense that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. To put it simply, black holes function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most alarming aspects of black hole research is that if someone were to fall into one, they would be stretched out into an elongated form due to the tidal forces acting on them. This stretching would happen gradually, and the person would perish before reaching the final phase of this process. So, let's be clear, it's best to avoid falling into one at all costs. Even though the nearest black hole is located some 500 light-years away, this still raises questions about the potential dangers they pose to us. In 2021, a remarkable milestone was achieved when scientists successfully captured the first clear image of a black hole. This particular black hole was located in the galaxy M87. The research team took multiple images over several nights, and by stitching these images together, they created a comprehensive picture that showed startling details. It turns out that a black hole is not simply one giant void of nothingness, as many people might think. In fact, a black hole consists of 3 distinct layers. The first layer is called the event horizon. Once an object crosses this boundary, there is no turning back, it will inevitably be drawn into the black hole. The second layer is referred to as the photon sphere, a region in which light itself can be trapped in orbit around the black hole. Any light entering this area will become ensnared by the black hole's gravitational force, unable to escape. The final layer is the singularity, where everything that falls into the black hole is crushed down to an infinitesimally small point. This is where the laws of physics as we know them break down entirely, making it impossible to predict what might occur. What is even more intriguing, and troubling, is that no two black holes are exactly the same. While they all adhere to this three-layer structure, the way they operate can differ dramatically from one to another. Normally, scientists rely on telescopes to observe celestial objects. However, when it comes to black holes, this method is not practical. Because black holes are invisible, scientists can only study them indirectly by observing the radiation they emit along with the surrounding gas and dust. Sending probes like Voyager to explore a black hole is out of the question, as anything that crosses the event horizon would be drawn into the singularity and obliterated. One theory for the formation of black holes is that they are the result of collapsing stars. When a star burns through all of its fuel, it can no longer generate the energy needed to counteract gravity, leading to a collapse inward that ultimately creates a singularity. In order to further investigate the nature of black holes, NASA scientists turned their focus to the core of the M87 galaxy. Here, astronomers observed an enormous whirlpool of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to fly apart, yet it remained intact. Scientists hypothesized that a colossal mass, between 2 and 3 billion times the mass of the Sun, was holding it together. This mass could only be explained by the presence of a black hole. Black holes may not just be created by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating black hole. Kerr's solution demonstrated that instead of collapsing into a point, a rotating black hole would form a thin disk, a phenomenon known as the ergosphere. Physicist Michio Kaku, a leading theoretical physicist, has been at the forefront of research exploring the mysteries of black holes and their possible connection to wormholes. His work suggests that understanding black holes could one day allow us to harness their incredible properties for space travel or even uncover new aspects of the fundamental structure of reality. One of the most fascinating implications of Kaku's research is the idea that black holes might not just be cosmic dead ends but could potentially serve as gateways to other regions of spacetime. The concept of a traversable wormhole, a passage that could allow for faster-than-light travel, has long been a staple of science fiction. However, some physicists believe that if exotic matter with negative energy exists, it might be possible to stabilize a wormhole long enough for something to pass through it. Despite these tantalizing possibilities, significant challenges remain. Current theories suggest that wormholes, if they exist, would likely be extremely unstable, collapsing before anything could travel through them. Additionally, the immense gravitational forces surrounding a black hole would make approaching one incredibly dangerous for any spacecraft or probe. Kaku has also explored the idea of using black holes as potential sources of energy. The rotational energy of a spinning black hole, for instance, could theoretically be harnessed using a process called the Penrose process. This method involves extracting energy from a rotating black hole by sending particles into its ergosphere, where they can split, with one half falling into the black hole while the other escapes with more energy than it initially had. If such technology could be developed, it might provide an almost limitless energy source for future civilizations. As our understanding of black holes deepens, new questions emerge. What lies beyond the event horizon? Could black holes be connected to white holes, hypothetical objects that expel matter instead of absorbing it? Do they play a role in the birth of new universes? Some physicists speculate that the singularity inside a black hole might not be the end of matter but a transition to another universe. Modern advancements in observational astronomy, such as the Event Horizon Telescope, continue to push the boundaries of what we know about black holes. The first ever direct image of a black hole, captured in 2019, was just the beginning. Future telescopes with greater resolution and sensitivity may reveal even more details about the mysterious objects lurking in the depths of space. As we move forward, the study of black holes remains one of the most exciting and challenging frontiers in physics. Whether they hold the key to interstellar travel, new dimensions, or the very fabric of spacetime itself, one thing is certain: black holes will continue to captivate the minds of scientists and dreamers alike for generations to come. Working on this unified theory for decades, one promising candidate is superstring theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is seen as a symphony, with different particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings warp the fabric of spacetime. Despite its promise, superstring theory remains highly speculative, as it requires extra dimensions of spacetime that we cannot directly observe. The additional dimensions could be so tiny that they are effectively invisible to us. Some theorists suggest that these dimensions were more prominent at the beginning of the universe during the Big Bang and that they collapsed as the universe expanded and cooled. Superstring theory's potential to explain black holes, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, black holes, and the cosmos itself, there's no doubt that there is much more to learn, and perhaps even more to discover, about the very nature of reality. As we stand on the precipice of such groundbreaking discoveries, one key realization remains: we are merely scratching the surface in terms of understanding black holes and their true nature. Michio Kaku's work in the field of string theory and the ideas surrounding quantum gravity have only begun to offer possible answers. Even though we've achieved greater clarity on the image of black holes through technological advances such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our grasp. The frontier of theoretical physics, specifically in the context of black holes and spacetime, is still an incredibly active area of research, where much speculation and exploration await. In addition to their obvious role in influencing the fabric of spacetime, black holes have become central to discussions about the origin of the universe itself. String theory suggests that collisions of universes could lead to the formation of new ones and that black holes could be integral in this process. Such a theory suggests that our universe might have been born from a collision of two previously existing universes, or perhaps even implies that we reside within a black hole itself, a concept that would certainly flip our understanding of the cosmos on its head. If this notion holds true, it could challenge everything we think we know about the Big Bang. We might begin to view black holes not just as destructive forces but as potentially creative ones that serve as gateways to other realms or parallel universes. While the idea that black holes could act as portals to other universes, or even enable time travel, is tantalizing, this concept remains within the realm of theoretical speculation. The mechanics behind wormholes and the ability to traverse them remain a profound mystery. Even if wormholes are stable enough to form, there is the question of whether the extreme radiation and gravitational forces near these structures would make them traversable. Some physicists speculate that if we could stabilize a wormhole, it might theoretically allow travel through time or between distant points in the universe, but that remains a far-off dream, at least with our current technology and understanding. Moreover, when we look at black holes through the lens of quantum mechanics, we find ourselves faced with even more intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales, and the laws of physics appear to break down entirely when we consider objects like black holes. This discrepancy between quantum mechanics and general relativity has been one of the most significant challenges in theoretical physics. Theories such as superstring theory offer a potential framework for reconciling these differences by introducing additional dimensions and offering new insights into the nature of gravity. However, this theory has yet to be experimentally verified, and many of its predictions remain untested. Theoretical physicists like Michio Kaku are working tirelessly to unite these two great pillars of physics, quantum mechanics and general relativity, into a unified theory that can explain the full spectrum of phenomena across all scales. Such a theory of everything would not only provide a deeper understanding of black holes and other exotic objects in the universe but could also illuminate the very nature of spacetime itself. The concept of multiple dimensions, as predicted by string theory, may help explain the unseen forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another area of intense study is the role that black holes play in the evolution of galaxies and the larger structure of the universe. The fact that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on galaxy formation and behavior. It is theorized that these black holes may regulate the growth of galaxies, control the rate of star formation, and even play a role in the eventual fate of the universe. The idea that black holes could have such an important role in shaping the universe adds another layer of complexity to their already mysterious nature. Moreover, the powerful radiation emitted by black holes, the so-called Hawking radiation, named after the famed physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a black hole. For years, scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes might emit radiation that slowly causes them to evaporate over time, potentially resolving the paradox. However, this remains an area of active research with no definitive answers yet. What is clear is that the study of black holes has not only provided us with remarkable insights into the nature of gravity, space-time, and the universe as a whole, but has also opened the door to a new frontier in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries. As our observational tools improve and as we delve deeper into the quantum and relativistic realms, it is likely that we will uncover even more surprises, reshaping our view of the cosmos in the process. As we push the boundaries of our understanding, new discoveries in quantum mechanics and astrophysics continue to challenge our existing models of reality. The study of black hole thermodynamics has introduced deep questions about the nature of entropy and information in the universe. If information is not lost in black holes, as some theories suggest, then it must be encoded in some form, perhaps through holographic principles, an idea that has gained traction in recent years. The holographic principle, proposed by physicist Gerard T. Hooft and later expanded upon by Leonard Susskind, suggests that all the information contained within a volume of space can be represented on its boundary. In the context of black holes, this implies that the information of everything that falls into a black hole may be encoded on its event horizon, rather than disappearing forever. If this principle holds true, it could have profound implications for the nature of spacetime itself, potentially leading to a deeper understanding of quantum gravity. Another fascinating aspect of black hole physics is the concept of firewalls, hypothetical structures of high-energy particles that may exist at the event horizon. The firewall paradox, proposed by physicists Almheri, Maroff, Polchinski, and Sully, AMPS, suggests that if quantum mechanics and relativity are both correct, then an observer falling into a black hole would encounter a wall of intense radiation, contradicting the classical idea that they would pass through the event horizon unscathed. This paradox remains unresolved, highlighting the need for a more complete theory of quantum gravity. Beyond the theoretical, observational breakthroughs have also reshaped our understanding of black holes. The first-ever image of a black hole, captured by the Event Horizon Telescope, EHT, in 2019, provided direct visual confirmation of the existence of event horizons. This groundbreaking image of the supermassive black hole in the galaxy M87 was a triumph of modern astrophysics, validating decades of theoretical predictions. Future observations may reveal even more surprises. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo have detected gravitational waves, ripples in spacetime caused by the collision of black holes, offering a new way to study these enigmatic objects. As technology improves, we may soon be able to observe the merger of primordial black holes, which could provide clues about the earliest moments of the universe. Some researchers even speculate that black holes might play a role in the search for dark matter, the mysterious substance that makes up most of the universe's mass. If primordial black holes formed in the early universe, they could contribute to the dark matter that shapes galaxies. Studying their properties may help unravel one of the greatest mysteries in modern cosmology. Looking further ahead, the idea of harnessing black holes for advanced technology remains a subject of both scientific inquiry and science fiction. Theorists have speculated about using rotating black holes as energy sources, or even as time machines, though these concepts remain speculative at best. If we ever gain the ability to manipulate spacetime on such scales, it could revolutionize our understanding of physics and open doors to possibilities we can scarcely imagine. In the end, black holes remain at the forefront of modern physics, offering profound insights into gravity, quantum mechanics, and the very structure of the universe. As we continue to explore their mysteries, we move closer to answering some of the most fundamental questions about our existence. The search for a unified theory of everything, one that reconciles the contradictions between quantum mechanics and general relativity, may ultimately hinge on our ability to fully understand black holes. With each discovery, we take another step toward unraveling the deepest secrets of the cosmos. Whether black holes serve as cosmic gateways, information vaults, or engines of creation and destruction, one thing is certain: they are among the most mysterious and fascinating objects in the universe, and their study will continue to shape the future of physics for generations to come.